Hello, this is David D. Hilster. I am a critical thinker, dissident scientist, and if you're not buying exactly what mainstream physics and cosmology are selling, then this is the place for you. There are thousands and thousands of scientists from around the world that have been working for decades outside the mainstream who have identified problems, fixed those problems, and who are proposing new theories and ideas. You won't find anything like this on the internet or on YouTube, so be sure you click below on the subscribe button and that little bell next to it so you'll be alerted when our next video drops. And of course, we're going to continue our talk with Mr. Stephan Hawking because it's bringing a lot of attention to physics and cosmology, good and bad. And the APS, which is the American Physical Society, has some very interesting information that was given to me by Stephen Crothers, who in my opinion is the best critical thinker of black holes on planet Earth today. Stephen Crothers is a real brilliant mind who happened to want to write and go to a mainstream physics university, who was kicked out because he was going against the black holes and their mathematics, which is a mess. And he continues to point this out, but now he's not the only one pointing it out. And that's what he's pointing out in his email chain he sent to all of us. And I thought I'd bring this to your attention. American Physical Society again. This is their little article they had just a number of days ago, March 14th. And it gives you a telltale sign that they're not exactly saying that Stephan Hawking was a great physicist. Let's read it here. And it says, Stephan Hawking, perhaps second only to Albert Einstein as the world's most well-known physicist, died on March 14th in Cambridge, UK. You notice that they didn't say the best physicist, a famous one even, or even a award-winning, whatever. They put Einstein and Hawking in a sort of not such a high place. Maybe the chink in the armor is starting to crack all around, including Mr. Albert Einstein, which, of course, those who follow this channel know that's a real problematic theory, the real theory of relativity. But it says among his peers, he was celebrated for his work on black holes and cosmology. Notice they said celebrated. They didn't say Nobel Prize winning. And, of course, Nobel Prize is given to a lot of bad science. And he was known the world over for his public lectures and explanations of science for general audiences. A Brief History in Time sold over 10 million copies worldwide. You notice, again, they didn't say it was a great book. They didn't say it was a beautiful book. They just said it's popular, and that he was known for his public lectures. Of course, if you go back to one of my earlier talks on Stephan Hawking, I picked out what I thought was the best review, at least in my own opinion, one that I would write on A Brief History of Time, and it was a 1 at best. And go back to that. That's a great little video I made there. And so let's go on. Now what happens is 7 days later, what do we find? Well, we find that we have an abstract given at the spring 2018 meeting on the 17th, just 3 days later, at the APS New England section of the APS for spring in Boston, Massachusetts. And this is under general physics, and it says, the title is Hawking Radiation, a Violation of the Zeroth Law of Thermodynamics. That is not good. Let me just put it. There are 4 laws of thermodynamics. Well, what is thermodynamics? It's a branch of physics concerned with heat and temperature and their relation to the forms of energy and work. The behavior of these quantities is governed by the 4 laws of thermodynamics. Okay, so I'm not going to get into that. You can read more about what thermodynamics is if you're not really up on it. There's something that we need to know for this particular criticism of Hawking's work, and that is intensive and extensive properties. Physical properties of matter and systems can often be categorized as being either intensive or extensive quantities, according to how much property changes, how the property changes when the size or extent of the system changes. According to the IUPAC, an intensive property is one whose magnitude is independent of the size of the system. An extensive property is one whose magnitude is additive for systems. Well, what does that really mean? Well, it's pretty simple. Here's an example. Now, this is from the slides from the talk this talk here, Hawking radiation. I have a link to that. So this is from the actual slides. I'll have a link so you can see them. They're not a whole lot there because it's pretty simple. And here are some intensive properties. Temperature, that is, the temperature of something really doesn't change by how much you have of it. The heat capacity, on the other hand, which you see in the other column at the bottom, does. That is, if you have two bricks and the brick can hold so much heat from the sun, if you have two of them, you're going to hold twice as much. So yeah, that is an extensive property. It changes with the amount you have. Of course, mass does. Of course it does. Energy, of course it does. Energy is a concept, but the concept of energy, the way we calculate it, does. Volume, absolutely. Intensive properties, though, like color, if I have a brick, it's blue, and I cut it in half, it's still blue. It does not change. So that's the idea. Density is a really important one. That is, density doesn't matter about how much I have. It is independent of how much of something I have in a system. So let's go into another slide that they talk about the intensive versus extensive properties. And what they say in this paper that is criticizing Mr. Hawking's work is saying that the concept of intensive and extensive properties is so important that Peter Landsberg wanted to make and establish it as the fourth law of thermodynamics. And you're going to say, wait a minute, if there's four laws, how could it be the fourth? It would be the fifth. Well, it is the fifth, but they label them 0 through 3, as we in computer science called zero numbered, where you start arrays. The first array that is, if you hold a list of stuff in what was called an array in computer science, the first one is 0. It's called zero numbered. So yeah, there'll be the fifth, but it would be called the fourth. But again, he's saying what's so important that the intensive and extensive properties, when you're talking specifically about thermodynamics, is really important. And so he would say that equations, intensive versus extensive properties, if one side of an equation is extensive or intensive, then the other, then so must be the other side. They sort of talk, of course, they sound more like Yoda. My master's in linguistics, I look at this as sort of like this formal university speak, but they're basically saying if it's extensive, it's got to be extensive on both sides of the equation. If it's intensive, it has to be intensive on both sides of the equation when it deals with thermodynamics, and that's why this one guy said we should have this as the fourth law of thermodynamics. So let's take a look at an example that we can sort of understand, and that is the gas law, the ideal gas law, which talks about pressure, and you get this equation, which is the pressure is equal to m, the mass, times r, universal gas constant, times T, which is a temperature, which is of course intensive, right? It doesn't matter what the how much you have it of tension, but then you have something like, we have molar mass. Well, that's a constant. The mass above it is what we have, which is the M. That's not italicized. That's the mass. That's extensive. Oh, that's not good. On the bottom we have a molar mass, which is a constant, and of course we have V, which is extensive. So we have, the problem was we have P, and we have all this other equation. We have M and V, which are violating. But if you take a look, that density, if you have mass over volume, that is a density. So if you replace this M here with this V over here and this top P equation, you have, in fact, P equals density over R over T. And what do you have then? You have P, which is in pressure, intensive, times the density. Density is mass over volume, but that density is intensive because it doesn't depend on how much you have. R is a constant and T is intensive, so you have intensive equals intensive. And so the world is copacetic, the world is happy in physics about that. But we take a look at the people who wrote this paper, and we're going to take a look about the entropy of a black hole. Now entropy deals with thermodynamics and all the things we can see here. We call entropy S. I'm not sure why that is. I'm not an expert in this area, but I do read a lot about this stuff. We have entropy of the black hole. That's what BH is, extensive. But if you look on the other side of the equation, you have K. That's Coulomb constant. C is speed of light. Cubed. Those are constant. K, C, constant. 4 times H, which is Planck's constant. That's a constant. G is the gravitational constant. G. So constant. That whole thing, all those little numbers are constant. You have a giant A. A is the area. Area is neither extensive nor intensive because it's a mathematical thing. And so if it's neither extensive or intensive, you have something that's extensive equal to something that has no extensive or intensive, because it's thermodynamics, according to these authors, And according to many people who study thermodynamics, they're saying this is a violation of something that we sort of all agree on, and that is intensive and extensive properties in equations have to match up on either side. You can't have intensive on one side and nondescript on the other. So that's one of the complaints they're making. Let's go to, and that's the entropy of a black hole. This all has to do with the radiation, or Hawking radiation. Okay, again, this is from their slides, from that paper I told you about. And this is the temperature equation. And of course, you have temperature, the Hawking temperature, and of course T, small big H for Hawking there, is intensive. Again, why is it intensive? Intensive properties have no change depending on how much you have, right? So it doesn't matter how much you have. Color the same way, temperature the same way. But the mass is extensive. So let's look at this equation. You have H, Planck, constant, speed of light, constant on top. You have 8, of course, is a numeric constant. Pi is a numeric constant. G is the gravitational constant. You have K, which is Coulomb constant, and you have M, which is mass. Mass is an extensive property. Is extensive. It is looked at as extensive, and temperature is not. Now they say photons emitted by a black hole are said to manifest a black body spectrum. This is not possible. It takes a physical lattice to produce such a spectrum, not simply thermal equilibrium with an enclosure. Now it's not really important that you understand all that, or that they really explain it to you. All that really matters in the big end of the game is that you understand a little bit more about thermodynamics, intensive, extensive, and you understand that people from the American Physical Society, who gave a paper 3 days after Hawking's death, are publishing a paper that says that his equation for the temperature and his equation for the entropy of black holes is not valid. These are invalid. They violate what they call sort of the fourth law of thermodynamics, which is extensive, intensive matching on sides of equation. Now, I want to step back one step back further as myself, who is a critical thinker, who have been around a lot of people who are not in the mainstream. These guys are in the mainstream, so the mainstream is even picking on poor old Stephen Hawking, and they don't seem to have a great necessarily opinion about Einstein, because I think some of them are starting to see chinks in that armor as well. That's why in that article before they didn't say the great and wonderful all-empowering Einstein. They just said a well-known, or worldwide well-known. So I am going to tell you and talk to you now about what we see as entropy outside the mainstream. And the person who I would point you to, one of my favorite, and you know who he is, Dr. Glenn Borchert, in my opinion, the best scientific philosopher out there of our generation, and maybe in many generations. And he has really great, if you haven't read his book, The 10 Assumptions of Science, or the Universal Worldview, his latest book, Infinity Universe Theory, Infinity Universe Theory. It's a great book. It's $10. It's super well worth it. Read it. I guarantee. But we're going to take a look at his look at entropy, because he, in my opinion, has got the best explanation of all these things, and we'll take a look at what he has. You notice it has little red lines under submicrocosms. That's because it's a word that they don't recognize in some of the, I think on, I'm using a PC here, and they don't know what that word is, but that's why that's underlined, so don't take any offense to that. But entropy, and this is Dr. Glenn Borchert, he says, the degree of divergence that exists among the submicrocosms within a microcosm. The opposite is negotropy, which is the degree of convergence that exists among the submicrocosms within a microcosm. Entropy, let's put it in a simpler way, which we will do it. Entropy increases when things go out of existence and decreases when things come into existence. This is discussed more later. This is in his glossary of his latest book. Again, you can get it on Amazon. I'll put a link down below for that, and you can take a look at that. And I also have a video. I believe we talked to him about his book, and that's a great interview. But this basically says that entropy is when things go out of existence and decrease, and in that when things go out of existence, it actually decreases. And things when come into existence, it actually increases. So it's not one of the things that we hear in the biggest difference I see is that in this type of definition, which I subscribe to because I've read his stuff, looking at all the evidence myself, critical thinker, that's what I want you to do too, don't take my word for it, I read it and I said, I do agree with this. I think this wholeheartedly. And that is, entropy isn't something that in mainstream science, like they say, is happening all the time and it's going one direction. And things are getting more complex and mixed up all the time. No. We actually have negentropy. Negentropy. Well, maybe that's how you say it. I'm not sure. But that's way he puts it. But basically, we see it as both directions. Things in the universe organize, and things in the universe get disorganized. So they get simpler and they get more complex, and that is processes happening all the time, nonstop, 24 hours a day, 7 days a week, forever. Which is 7 days a week and then forever. That's a huge leap, but that's the leap it has. But like I said, all the time, like I say to everybody, don't take my word for it. Now you know that, in fact, Stephan Hawking, even amongst his peers, this is one of the reasons he didn't win a Nobel Prize. And of course, we know he's now being sort of put together with Einstein, and people are starting to maybe think maybe the super worshiping that goes on that we have of these people, and we have those physics evangelists out there who super worship, and if you try to even say Einstein is wrong, you get your head bit off, like or laughed at, like Neil deGrasse Tyson, one of my least, unfortunately, favorite people out there, because I think it does a lot worse for science and critical thinkers, because he preaches what he says is truth, and then he pretends to let you think about it. But ha ha ha, if you don't understand it, you're stupid. Or ha ha ha, if you criticize it and have evidence against it, you are also stupid. And like I said, if you take my word for it, anybody's worth on faith, you're in trouble. Don't do that. Stay critical, stay thinking. I'm Dave D. Hilster. I am your science therapist. Ciao for now.